Okay, so we have one person joining in. Okay, hi Manohar. So welcome to this week 9 TS session on optimization methods for civil engineering. So in today's session, I'll be discussing about the R programming mostly. So I don't have any slides or anything. I'll directly go into the R coding and solve some problems similar to what you have seen in the class as well as similar to what you will get in your assignments. So in today's class, since I'll be going into the R studio screen directly, so probably my video won't be open when I record it. So I guess that's fine. But yeah, let's go ahead with the class. So I won't be going into much detail of introduction to R part that Sir has already discussed. So I think you all will be familiar with how to download this both R and R Studio and then install the packages that you require. Did you face any issue, Manohar, while installing or anything, loading packages or anything? Uh, okay, okay, great. Yeah, so while I was loading the packages and installing it, I faced some issues because I had R installed in my laptop previously. So while I was trying to install that GA package, it threw me some error. So you might face some issues if you're having a previous version of R or there is some version mismatch of the packages and also the version of RStudio that you have. So be careful with that. So what I did then is uninstall and installed everything from like scratch, and then it worked kind of. So yeah, so I'm not going into the details of installing RStudio and R and also installing packages. I think that have been covered thoroughly in the class itself. So yeah, yeah, go ahead. Uh, no, you don't need to purchase anything. You just have to put install that dot packages G and you need to have internet connection. So it will download automatically from the internet itself. Yeah. All right. So yeah, any more doubts you can ask related to art? Otherwise, I'll just look at some of the problems that Sir has already solved in the class, and then I'll go to the similar problems to the assignment. So let's share my screen. Okay. So right, I guess this has been being recorded. Yeah. So that's fine. All right. Yeah, I hope my R Studio screen is visible. So let me go ahead with that. So these are first few examples are directly from the class itself. So just for the sake of completeness and understanding, let's go through this once more before I go into the assignment specifically. So this first line tells you to install the package, which is for genetic algorithm. Install.packages is the command and GA is the package name, and you have to install it. And since I have already installed it in my RStudio on my laptop, so I won't be installing it again. So I have commented it out. So hash is the comment version of kind of in RStudio. So now what you can do, you can load this package. For that, you can click run on that line. So this library.ga kind of loads your package GA. So if you go to packages in this site, you can see that this GA has been ticked marked now. So that means you have successfully loaded your package. If there is some issue like GA is not available here in this system library, that means you haven't installed it correctly so far, or if it's not tick mark, you can tell that you haven't loaded it properly as well. All right. So for me, it's perfectly fine. So I'll move on to the single variable optimization problem first, the unconstrained version of it. And We'll be solving it using this GA package by this genetic algorithm method. So in R, what you have is, suppose you want to write a function. So for that, what you have to do this, use this function keyword. And then this x is the argument. It kind of tells you that this is a function of x that you will be writing. And this is the expression of the function, which is x squared plus x times cos x, then plus sine x squared plus sine to the power, uh, sorry, x to the power sine x. So this is your function. So let me run this line. So now your function is kind of loaded in the environment. Next, what you can do, you can plot the curve. So this y level gives you along the y-axis, this fx will be there, and along the x-axis, those x will variable will be there. And you kind of plot it in the ranges of 0 to 100, and let's see how this plot looks like. So let me run this line. So yeah, so this x value goes from 0 to 100, and this is how your plot looks like. So I think one of you asked this, how are you generating these plots previously in a class and also in the discussion forum. So all these plots have been generated in Python and mostly in this course, and you can also plot this in MATLAB or Python or any other programming language as well. All right. So next is this function, which you can use or you may or may not use. So this monitor kind of allows you to monitor the genetic algorithm progress. So your how your solution changes from kind of one generation to another. And so we want to, if we want to visualize that, you need this function. So it's kind of standard way of writing it. You kind of define one function and pass this obj, and kind of this generation equals to obj at iter. Iter means some iterations. And then this points kinds of plots those population versus this fitness function value. And this is kind of your color, and then this function again will actually plot this, and then the sys.sleep function will kind of lets the system sleep for a few seconds, and then it will kind of show up, so that animation kinds of goes to. So if you want to run the entire thing, you can just select it and then click on run. So I have already run this portion. Now let's move into the main part of it, the genetic algorithm part. So for that, you have to use this GA function, and you have to give the type. So this is the real encoded genetic algorithm, your fitness function. Since you are maximizing it, it's f anyway, and your this is your lower limit for x, this is your upper limit for x. And this is the monitor equals to monitor function. This kind of lets you to monitor the progress of the solutions across generations. So let's run this line and see what you get. So yeah, this visualization, it's, I think you can see that this is your global optima somewhere here. So let's see if we can get to that. So I'm running it for 100 generations. I think that's default. So let's see, it will run for some time. Yeah, all right. So your solution is kind of bunched up near the global maxima itself. So if you just run the next line summary GA, it gives you the solution point as well, this 94.2659. So this is your global maxima, which you have got. That G at solution kind of prints the solution value. AB line is a function which lets you draw straight lines. So you want to join this by a vertical line. So that you will be doing, and this red line appeared. Then this points function is kind of tells you the fitness versus the generation kind of plot. So you will be able to see this. Yeah, so this fitness versus generation curves appears, and you can see that around 40 iterations it kind of converged. So this is one simple example of genetic algorithm using single variable function. And let's move on to the multivariable GA. Let's just see one example for it. For that, I will comment the other things out, which is not required by the previous problem. So Control Shift C is the command for like commenting the entire part if you want to comment it in entirety. So this monitor is also was specific to the previous problem. So let's comment it out. This one also, let's comment it out. All right. So now you have to also load this GA package, but I have already loaded it, so you need not do anything with that. So let's move on to this second part, the multivariable GA. For that, let's uncomment this part and see. So this is the first your function. So if your function is of multiple variables, you can use this kind of a scalar type notation like x1 and x2 and write it like this. Or you can use one vector x and then you can use x of 1 and x of 2 to denote those two variables. Either way is fine. So let me first do this. Then this x1, x2, and then the sequence function kinds of gives all the values like from -6 to +6. So this is lower bound and upper bound. And this is the interval, which is 0.1. So this is just to get the function values and get the plots at those points. So this fp will be the function value at the grid points, and this p or e pers function is another way of plotting this and get a view of the function. So this is kind of a 3D view. And then, yeah, this is appeared. And then the contour plot, you can also do that. So, yeah. So this is your contour plot. So this is all about plotting, and I think you have already seen this in the class. The next one is this monitor function. So this one I require for this problem. So it's kind of similar to the previous one as well, but you have to just define this, be careful with the points. So you have two mm, like inputs here for multivariable functions. So that's why this is written like this. So that's the only change that's in here. And this one is another change, x1 and x2. So let me just select the entire thing and run this for once. And finally, I have to run the genetic algorithm part. So I'll uncomment this portion. So let's run the first line. Then what you will get is just the function first. Then you have this part of genetic algorithm. So this is real valued GA, and fitness function is again f because you are maximizing it. You have the lower limits of -6 and -6 for both those variables x1 and x2. This is your upper limit. Population size that I'm using is 100, and this monitor equals monitor kind of lets you to monitor the progress. All right, so this is the generation one, and you can see that at first the points are kind of scattered, and there are kind of four optimal, the local optima. So it can go to either quadrant. So let's see where you are getting the solution. So it will take maybe few seconds to run around, or maybe 1 minute to run. So yeah, let's complete this exercise quickly. Yeah, any doubt with this portion, you can ask. I think it's pretty simple. You have to, I don't think sir has shared this code with you, but you can just write it down and just replicate what sir did and to just to check whether everything is working fine, and then you can go ahead with the assignment problems and all. And also, I think the assignment problems are pretty simple this week. Like something is given, some input is given, what's the output or something like that has been asked. So you can directly put it into R and get the answer. So not a problem with that. Yeah, so it's around 60 generations that you are kind of in this quadrant. So this is in the first quadrant. Yeah, so it's so you can solve any problem with this. You have to just change the function expression, the lower limits, the upper limits, population size you can define on your own. So it's not a problem to solve an unconstrained optimization problem with the GA and uh, whether it's a single variable or multivariable. Yeah, it's almost done. Yeah, so it's done. Let's see the solution that you have got. So let's run this line and then this. So this is the red point, which is your solution point. And then the summary GA kind of gives you. So it's 2.99 and 2.00. So the actual optimal is at 3 and 2. So it kind of got the value. And this GA solution again prints the x1 and x2 value at optimality. So you will get near optimal solutions using this. So if you use more population size or maybe some more precision techniques, then you will get the actual value. All right, so let's get into the second example. So this one is again, I think, pretty similar, also covered in the class. I'll probably not run the entire thing again, or let's see if there is some difference between this and the previous one. So in this example, so I have already loaded this GA, that's fine. So this is function x1 minus 2 square plus x2 minus 1 square. And it's both this variable is within minus 5 and plus 5. And let's see what's the maximum that you can get in this kind of problem. But so this is the function that you are minimizing here. Yeah. So the basic difference here is that since you are trying to maximize your fitness function value, so when you do this, you need to put this minus sign so that you maximize the negative of that. So you have to be careful. And the optimal value should be here in this case because this is the sum of two square terms. So should be 2 and 1. So let's see if we can get this. So I'll just quickly run this part. So I think you have already seen this, how to plot this and all. So let's quickly do this. So first is the unconstrained problems. I think I have drawn the constraints as well. So let's draw till this point. Yeah. Yeah, so for the unconstrained problem, you should get the solution at 2 and 1, but in the constrained version, things will change. So first, let's see the unconstrained one. So you put this function, you run this line, and then what you have to do, you have to just run this GA algorithm. So I'll just decrease this population size, probably 100, iterations 100, and it's, let's see. I'm not monitoring anything because I don't have the monitor function, but let's see. Yeah, we got the solution, which is 2 and 1. Very close to that, you have got the solution. So let's get the constraint version of it. So you have the function and you can plot the constraints as well. So let me do this thing. So you have this two constraints. One is this curve, and another is the straight line. And for that, in the constrained version, you have this f1, which is your original function, but with a negative sign, since you were maximizing the negative of the original function. This g1 and g2 is just an expression of the left-hand side of the constraint. And then you have to put this expression where this g1 less than equals to 0 and g2 less than equals to 0. So those are your constraint, both has to satisfy. F1 is your function, and this minus this one E4 is kind of gives you the constraint violation. So if you're violating, you are accumulating those much objectives in the in the objective function. So let's run this part, and now we can run the G algorithm part where this if kind of takes care of everything with this constraints. Yeah, now the solution is different, 0.93 and 0.98. If we run it again, we'll probably get another solution. But I think the actual one could be around close to 1 and 1. And yeah, you were getting very close to that. Yeah, so I think it's easy to solve this both unconstrained and constrained problem. You have already seen this in the class. So let's see what's there in the third example here. So in this third example, it's again pretty similar to what we have seen before. I think it's just a function that's kind of different. So it's now 3x1 square minus 2x2. So again, I have already loaded the GA library and this function has been defined. X1, X2, this limits have been kind of defined and also the grid points are defined. Then you kind of combine it and get the function values and on those grid points and you to draw the contours of that. So let's run this tree line first. Yeah, so you will get this contour plot and this is without any constraint. So let's run the unconstrained part. So let's run this part first. And then it's just running the GA again. So let me again reduce this 100 and 100. Yeah, and notice that the syntax and all, it's almost the same. We have to just be careful with the upper limits, lower limits, the function expression, and the parameters that you kind of choose. So yeah, I can run multiple times and see. So probably it will be close to 0 and 5. So you are getting that. And let's solve the constraint part of it. So let's do this. Yeah, these are your two constraints. And as before, your constraints are less than equals to type. If you write it in terms of this G1 and G2. So let me run this part and you can run this GA solution. Yeah, now we were getting some different solution minus 0.22. So this is the red point which have been marked as your constraint optimization solution, near optimal solution that you have got. It's different from 0 and 5 that you have seen before. And if you run it multiple times, you'll probably get different solutions and they will be close to each other. But since the population that you are dealing with is kind of random, so we'll get different solution every time. All right, so there's three problems that we have seen so far. It's simple and you have already seen this unconstrained and constraint optimization, maybe single or multivariable. So everything is kind of easy. Okay, so let's move on to the next example pretty quickly. So next one is also pretty similar. You have a function given and you have those upper bounds and lower bounds. And this is again the same thing, but now you can monitor the progress. So I have just added the monitor function, and this function is kind of written differently. So whenever you are writing function of x, you can give this as a vector and use x1, x of 1 and x of 2 as your two variables. So as before, this first part is simple. Your plot is like this. This is the unconstrained part, and this f is your function. And let me run this monitor part. So this monitor part is simple. It's pretty similar to what we have seen before, but uh, now you have an extra thing here. So let me actually run the constraint part itself because that will complicate things otherwise. So let's run from here itself. All right. So next is this monitor part. You have this extra line here, which tells you this constraint, which is x1, 2x1 plus x2 less than equals to 2 probably. Yeah, g1 is less than equals to 0. So 2x1 plus x2 minus 2 is less than equals to 0. So let's run this part. And then this, again, you have to put it in terms of the constraints itself. So let's do this. Yeah. Now after this, I have just put this monitor equals to monitor. So this population size I can put as 100 and maximum iteration, let's put it as 100 and let's run this and see what you get. So since I'm monitoring it, so let's run this one first. Yeah, yeah. So initially you have all these points scattered around and you should get a solution which does not cross this straight line. So we should be getting somewhere here. So let's see. So this is generation 13, 15. Okay. Yeah, it will take probably a minute to run. So let's see what you get from here. Yeah, after this, I think I have one more example, and then, like from the class itself, then we'll move on to the assignment questions directly. Like, just I'll tweak some numbers here and there and see the similar results that you can get. So I think everyone will be able to solve all the questions of this assignment because you just need to put it in the R and you will see the solution itself. So it's good, better that you just understand the logic and how you can solve some unknown problems because even in couple of problems, I think the codes are also given. But yeah, you should be able to write your own codes by looking at all this. That's almost uh, over, and around here you should get your that red marked point, which is the optimal solution. Yes, so it's done. Let's mark this. So this is the red point I was talking about. It appeared on this straight line, very close to that. And then this is your summary. This is your optimal value 0.11 and 1.77. And finally, if you print the solution, you will get the same thing. All right. So I think you have understood these problems. Oh, you have, yeah, go ahead, Manohar. I see your raised hand. Yeah. 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 Yes. Uh, your voice got cut off. Can you repeat? Yeah, this line number 20. Yeah, yeah. So there is the difference. So suppose you are writing this function keyword is there, right? So suppose you are using multivariable function and you are passing one argument, which is x here. So that means x of this square bracket of 1 will denote your x1 and x of your square bracket of 2 will denote your x2. So if I had written here x1 comma x2 and then replaced all this with x1 and this one with x2 and probably this one with x1 and this one with just x2, then it would have run fine as well. So there are two ways of writing it. This one is kind of scalar kind of notation where you are specifying every argument, and this is kind of your vector notation, and that's why you are using the first. Uh, you can think of it as an array or something. You are just using the first entry of it, and this is the second entry of it. So that's why you have to specifically write your square brackets here if you pass one argument from. Is that clear, or should I just? Oh, okay. Yeah, so that's great. Yeah, you can ask other questions as well if you have doubt with specific syntaxes and all. Yeah, I will try to get those doubts clear. All right, so what else I have? Yeah, the next problem I can move to that. So let's do that. Yeah, so this is the assignment kind of problem itself. So I won't be like directly solving it, but probably similar things I'll solve here. So I'll probably, so since I don't have any slides or anything in today's class, since I don't require it, I'll just probably just write the question briefly here and just see, give you the solution. I'll just take a look at the solution later on. I'll probably share this script with you later and you can work it out with the problems that you have. Okay, so let's first solve the first question. So what will be the output of the following? So, so I think it's pretty simple. Like I'm kind of spoon feeding everything, but there is nothing much to discuss here in this class itself. So, no, when you run this, suppose I run this line. So let me first clear everything from here. Let's do this. Plots I can maybe clear later. All right, so let's solve this. So suppose I run this line, this x that kind of stores this 1 to 7. It's kind of storing some vector. So you can see that it stores 1, 2, 3, 4, 5, 6 up until 7. So it's kind of little bit different with Python. So if you have seen Python, it kind of in Python, it's this last one is not taken. It counts till 6, but here there is some difference in R. It's 1 to 7 and everything gets counted. Then suppose I make it as 7 to 1. So by default, it will take a step of -1 from here. So if you run this, you get this 7, 6, 5, 4, 3, 2, 1. So those are some basic difference. Then similarly with y variables itself. So let's try with something else. Suppose write it as -8. And yeah, this will again go till up until -8. Now, if you want these two vectors and kind of you want to subtract one from another, then their dimension has to be equal. It's like 1 cross 7, first one, and second one is 1 cross 12. So let's make it same. So let's use -3 here and let's run y again. Yeah, so you have those both these vectors, which is x and y, and it kinds of having the same dimension. And let's try and see what z is. So z is x minus y, and it's just the subtraction element by element. So it's 7 minus 3 is 4, 6 minus 2 is 4, and so on. And that's why you got all 4. So I think in one of the question, this will be asked like, what is the output of the following? And some x and y is given, and you can just directly put it in R and just see what is the output. Right. So next is again similar. So there are two lines of it. So again, what's the output that's being asked? So what is the output of the following? So let's make it more interesting. 6, 5. Right. So suppose I've given you this. So let's see what you will get. So as before, if you run this 3 colon 6, that means you will get 3, 4, 5, 6 as your x. Let me clear this. Yeah, you will get 3, 4, 5, 6. If you run this line, it kinds of gives you, this is some conditional statement. So it kinds of checks whether all these elements here in this vector, say x, is greater than 5 or not. So if you check the first one, it should be giving you one statement which is false. This one should also give you false. This should give you false. And since 6 is greater than 5, you should get true. So if you run this, yeah, you will get this output, false, 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 and true. So I think this question, I think the third problem, I think none of the answers actually match with what you will get actually. So I think there is something wrong with the options itself. So yeah, we'll probably tell the main TA about this because yeah, I see all falses written there, but it's not the actual thing. All right, so this is another, and then probably we'll get some theoretical questions which you can answer easily. So let's see the next one. Again, it's dealing with matrices. So what is the output of the following as before? I will just write this block as well. All right. So if you just store this x and then you store this matrix and write colon x, it kind of prints out x itself in this console. So that's why I've written this colon x. Otherwise, you can check from here itself in this environment. And yeah, so I think in the question itself, it was written like that. So let's use some different numbers maybe. Let's say, just say 4. Let's see what we get. Yeah. So if you write run this, what you will get is that this 4, it is the number of rows that you are using in the matrix. 2 is the number of columns that you are using in the matrix. So that's why you can see this 4 rows and 2 columns. And how these values are kind of arranged, that information is kind of given from this 1 colon 8. So these are kind of stored across this first column. These values will be stored in this column first, and then it will move to the next column. So that's why it's 1, 2, 3, 4, 5, 6, 7, 8. So if I had made this something different, suppose 1 colon 16, let's see what happens. Yeah, there is this warning that you will get that this size, so you have given the 16 inputs here, but actually your matrix takes 8 inputs. So this 16 is not equals to 8. So that a warning message you will get, but it will store it as the matrix from 1 to 8. Right. So let's deal with something different. So let's see if this works. Yeah. So this is also fine. So it's from 3 to 10. So in the next one, it is again, this is a 3 by 2 matrix, and it kinds of have some repetitions in it, which is 10, comma 6. So let's move these numbers around and see what you will get. Okay. Yeah, so there is some mismatch that you have got. So this data length 6 is not sum multiple or multiple of the number of rows. So this has to be different. So here you have to have 8 values. So this is the number of repetitions of those values, and this is the actual value that will be repeated. So if you do that, yeah, you will get this all 12s, and all these 8 values are 12s now. So now we can take a product of this two. So this is x times y. So if you do that, let's see what you will get. So you will get this 36, 84, this 48, and all these things. So basically what you have two matrices of dimensions 2 cross 2. You are multiplying, sorry, it's not 2 cross 2, it's 4 cross 2. Yes, and then you are kind of multiplying it and you are getting another matrix. So I think this multiplication is it's kind of element by element multiplication. So this 3 times 12 has been stored here, 36. Then you have this 4 times 12, which is 48. This 5 times 12 is 60. Then the 6 times 12 is 72. And then you have this all this multiples of 12 up until the last value, which is 10. So 10 times 12 is 120. So this is this x. multiplied by y by this sign if you write this kind of star. So it's element by element multiplication. It's not the actual matrix multiplication because the dimensions, it's not the same, like the number of columns of x is not equals to the number of rows of y here. So anyway, you would have got an error even if you had tried to do a matrix multiplication. So I think, yeah, you can solve such problems easily again. So let's see, there is another problem which has these two vectors m and n, and you have to get again m times n. It's pretty similar to what we had before, but this time with factors. So what is the code of the one? So let's change this numbers. Okay, so if you run this first one, what you will get is just this 1 cross 3 vector 462. So let me add another here, so probably 7. Yeah, you get 4627. If you run n, you will get 283. And now you are again kind of element by element multiplying this, but the dimensions are not the same. They will get this warning message again. This longer object length is not a multiple of the shorter object length. So this 4 times 2 is happening, it's 8. 6 times 8 is happening, that's 48. 2 times 3 is 6. And then when you have this element 7, then it will again go back to the first element and it will multiply that 7 with 2. So we'll get the answer as 14. But this 8 and 3 is kind of not repeating again. So it's, if you had another two, say, elements in capital M, then this warning message should not have appeared. So let's see if that is the case anyway. So let's run the entire thing together. Yeah, you don't get any warning message, and there you'll have this 8 times 1, which is 8, and 3 times 2 is 6. Those are the two extra elements that you have, right? Right, so it's pretty simple. Then you have something about date. That's just to calculate the difference, time difference between two dates. So it's again simple. Let's use something else probably. All right, so this is the first date, which is X that will be stored. So X now is this time actually, 4th of March 2020. This one is Y is 27th of February 2020, and you were just taking a difference of this two. So it tells you the time difference of 6 days. So I think 2020 was a leap year, so you had 29 days, and it's 2 plus 4, so that's 6 days. So it's again simple. You don't even need R to like answer these questions anyway, so you can do it on yourself itself. So not a problem. So let me see what happens when you have some yearly difference. Like, okay. Oh, I haven't run the entire thing. Yeah, it gives you the answer in days itself. So you get 736 days. All right. So this is, I think, again, pretty simple. Next is, yeah, it's your question 9, I guess, in your assignment. And I think the code is given itself. So you have to find the location of the maximum using the code. So you can just copy paste the code and that should work. So anyway, what's being done there? It's let me just change the limits of it. Maybe it's minus 3 and 3. So again, you can have this GA package loaded. Then you have just one single variable function, and you can just write x here, and x will itself be a scalar here because we are dealing with single variables. And this is some function sine 3x plus 45 sine square 3x plus 45, then 0.9 sine cube of 9x and something. So you can just write the function. It's not that difficult. And probably this can be minus 3 to 3. So let's run this. So this is your function. This is your curve. Yeah, so you have drawn it from minus 3 to plus 3. And then, as before, we just have a simple monitor function. So let me just change the limits a bit. And the rest of the things will be pretty similar to what you had before. So you can just run this part. And then it's all about this GA. So this lower and upper limit, let me adjust it a bit. And yeah, let's see what you get when you run this. Yeah, so your solution is kind of all over the place at the beginning. You should get uh, your maxima should be around here. And I think it default value of iterations, the number of iterations is 100. So let's see what you get. Yeah, so let's get into the summary. So that's minus 1.94. Around here you get the maxima. All right, so I think even with changing the limits, you would probably you'll get the same answer or something. So let's do something else as well. Okay, so this monitor GA, it's not, I guess, required. Anyway, yeah, it's not required. It was there itself, and then you have this AB line drawn here through that point. Okay, so since it's at minus 1.94 something, let's see what happens if you put uh, this as minus 1 and plus 1. Then suppose you will get a different answer to this problem. We'll just quickly run this part. So this part has to change. Then this is the same. This is also same. Yeah, yeah. Let's run the entire thing again. Yeah, now you should get a solution, either this one or this one. I'm not sure. Probably this one is a little bit higher. But this one, let's see. Or maybe it could be symmetric in that portion. I'm not sure about that. Probably your solution is around here. Yeah, now your solution is actually here, minus 0.52. And your fitness function value should have been, I think, close to 0, but nonetheless, for 100 iterations, you got close to 0, I guess, 2.07. Or did you have, no, it should have been close to 0. Anyway. Okay, so this is all about the question 9. So you can solve it by the code that has been given to you. So let's move on to the next one. Mm, yeah, this is, yeah, I think this problem had some issues with uh, Yeah, there is one issue in this problem. So there was a typo here. So this question number 10 is also having some issues. So in the problem itself, I think it was given sine 2 pi x divided by x minus cos 2 pi x times x. But in the code, here it's not written as 2 pi x. Here it's written cos 3 times 3 pi x. So probably we have to get this question sorted as well. So I'll talk with the main T about it, and probably it. I don't know what is the actual thing, whether this will be two or three. So maybe by looking at the options, you can guess something, whichever is in the option, or if there are two solutions, both are in the options, then that will be confusing again. So let's see what you will get from here. So when it is 3 pi x, the code that have been provided here itself, so if you run that, so this, let's run this f, let's run this curve. So this is how it looks like. Then this is the monitor function, and this is your GA. Yeah, let's see what is the solution that you are getting, because anyway there will be confusion regarding this question. So let's get it done here itself, whether that's 3 or 2. Let's check that. Right, so let's run the summary. Yeah, we're getting a solution of 0.4248. So that's in the solution itself. So I think it should be 3 pi x then. But if you run with 2 pi x, let's see what is the solution that you are getting, whether that's in the options or not. So let's run the entire thing quickly. This monitor, I don't think I need to run it again, but let's run it just for the sake of it. Yeah, so let's see. It's easy when the code is given to you, but I think you can. It's just about replacing the function and adjusting the limits and the arguments that you need to fix. That's the main thing you have to learn here. Yeah, so from here, you are getting a solution of 0.296. So that's not in the answer. Yeah, so I think the 3 pi x is the correct one for the cos. I'll just write it as 3 here for the reference later. Okay. Yeah, so this is all about this question. Then you have, yeah, question 11, which is again pretty simple. So the function is again given. So since this is a multivariable function, since you are passing one argument, you have to write x2 in brackets or x1. And then let's run this. Then you can directly run the GA by this limits and everything. So let's quickly run this and see what is the solution we're getting. Yeah, by 100, after 100 iteration, your best solution it's like minus 0.08. So, and your mean is around minus 12.9. So that's the fitness function value. And this is your solution value, 0.71 and uh, 0.53. So I think in this problem, what's being asked is to write the solution, yeah, compute the minimum location of the function. So probably we're not getting the correct one from here, because there could be some issues with the population size and everything that you are using. So summary GA here. Now it gives you around 1 and 1. So it depends. So whenever you're solving such problems, it might happen that you are not getting the one that's there in the options itself, but you'll probably get something very close to that, like 0.996 and 1.0004. So you can say that it's around 1 and 1, but by looking at 0.96 and 0.92, it's kind of hard to tell whether it's itself at 1 and 1 or not. But yeah, just run multiple times and check which one is the closest and report that answer. Yeah, so let me change this a bit. Maybe the function I can use is 9, this is 2. Let's see what's the answer that you are getting now. Yeah, so you're getting some different answer. It's kind of all over the place. But yeah, when you solve the actual problem, you just be careful by putting the values in the correct places. All right, so I have around 4 minutes and I have, I think, some two, three questions more to solve. So let's move ahead. So this is again pretty similar to before. So you have this GA function, and let's run this quickly. Again, the sequence is this first function contours. So this has already been told in today's class. This monitor functions and this one, everything has been discussed. So I'll just directly go to this GA summary, but yeah, I think I've kind of given you the answer here. I don't want to give the answer directly, so let's move this up a bit. So this is 3. Yeah, so that should give you a different answer. So let's quickly run this and see what he did. All right, what you have is 13, 14, and 15. All are similar problems. So I think I'll just quickly change this things a bit. Uh, so do you have like any more questions you can ask right now? Otherwise, yeah, I'll just give you these two examples and we'll wrap it up. And we'll probably share this script only, this file, because this is kind of useful for your assignment. Others you can get it from the class itself. Okay. So make this a bit interesting. Yeah, it's turning. So it's kind of converging around this location. So let's see. 1, 8, and 4. Yeah, so you got the answer 2.46 and minus this thing, right? So I think I've run out of time. So yeah, anyway, the last three problems also, you can check it out. I think the codes kind of so I don't want to give you the codes for questions 14 and 15 since that's not given in the question. So let me remove it, but I think you can get it later from this video itself. So that's not a problem. So if you're smart enough, you'll be able to solve it. So, and the rest of the things, I think you can do it on your own. So it's around almost 4 now. So I think if you have any question, you may ask. Otherwise, I'll stop for today. So any doubts or anything related to our you can ask. Otherwise, you can join the other session. Okay. Yeah. All right. Then you can join the other session.